Right, good evening. The last week we discussed the forecasting, the ARIMA model. Also, I have uploaded the empirical research paper relating to the ARIMA model. Right, please read how to use ARIMA model for forecasting. ARIMA model is used for forecasting. Right, in this article shows how the forecasting the real GDP rate through econometric model. The article use to analyze the data or forecasting the data, the ARIMA model. So then one means AR, auto regression. Middle, that one means number of integration, and the last one shows MA, moving average. Right, then this is the way we use to analyze or for forecasting GDP growth. In this case, ARIMA model, the Box-Jenkins methodology is used. Most researchers used Box-Jenkins methodology. What is Box-Jenkins methodology? Is the combination of AR, that means auto-regressive, and the MA, that is moving average model, as follows. See this equation. Y means GDP growth. Beta 0 is intercept of the model. Beta 1, YT minus 1 is the lag value of the dependent variable. Our dependent variable is GDP. Then YT minus 1 means the previous year, last year GDP. And up to the number of lags, T minus 1, T minus 2, T minus 3, T minus P, up to the P. After that, it is errors. Errors, last year errors, lag error, 2 lags up to the Q lags. Then the total current error term. The Box-Jenkins methodology consists of following stages. First stage is establishment of the stationary of time series. Stationary of time series. For this purpose, we check the autocorrelation function ACF as well as augmented Dickey-Fuller test ADF and Philip-Perron test PP are used for stationarity testing of time series. Right, what are the tests we use to test stationarity? First one is autocorrelation function, other one is augmented Dickey-Fuller test, then other one is Philip-Perron test. The model identification, right after that, we need to identify the model, the ARIMA, not ARIMA, AMA, a autoregressive moving average. P means number of autoregressions, Q means number of moving averages. To determine the order of autoregression and moving averages, P and Q, we use sample of the autocorrelation function. So then how many number of order, how many autoregressions, how many moving averages to include to the model depends on the autocorrelation function and the partial autocorrelation function, ACF and PACF of the stationary series. These two plots, there are plots in the autocorrelation function and partial autocorrelation function. These two plots are suggesting the model we should build. Right? So then next, after that, after determining the order of autoregression moving averages, that means after determining the P and Q, then we estimate the model. The involvement of the white noise term of the ARIMA model entails a nonlinear iterative process in the estimation of the parameters. That maximum likelihood estimation is generally the preferred techniques. Then next step is diagnostic check-in of the model. With a diagnostic check-in, we investigate whether the estimated model acceptable or statistically significant, or whether the data, so our model fit to the data. The Box-Jenkins for the adequacy of estimated ARIMA model suggested checking the randomness of the residuals. Right. Then the next step is forecasting. Right. Those are the methodology of the. This is the phases or steps in Box-Jenkins ARIMA model methodology. Following the methodology, first our task is to check the first one is to check the stationarity, establishment of the stationarity of the time series. How to check? By using the autocorrelation function and augmented Dickey-Fuller test and the Philip-Perron test. Right. In this testing a stationarity, this test, there are 16 legs. There are 16 legs, 1, 2, 3, 4, 5, 6, 7, up to 16. There are 16 legs in levels for fresh differences. From this figure, we can conclude that the coefficient of the autocorrelation function ACF begin with high values and decline slowly. It starts from high values and decline slowly, indicating that series are non-stationary. Also, Q statistics at the 16th leg, 16th leg, Q stat of the 16th leg has a probability value. Probability value correspond to the Q stat 0, which is smaller than the 5%. So we cannot reject null hypothesis that real GDP data series is non-stationary. Then the series must be configured in, we cannot reject, that means we accept the real GDP data series are non-stationary. Then because the series are non-stationary, we need to consider the first difference to convert the series to the stationary. This is levels. See, in the correlogram of real GDP rate series, it's levels. Then the correlogram of real GDP rate series of first differences. Now the same results. We convert the data to the first difference and see whether the series are stationary or not. Now see the probability value of the correlation and the partial autocorrelation. We conclude that Q statistics of this column at the 16th leg has a probability value is greater than the, it is probability value larger than the 0.05. So then we cannot reject the null hypothesis that the real GDP rate series are stationary. The results of augmented Dickey-Fuller test, you can do the same by using the augmented Dickey-Fuller test as well as the Philip-Perron test to check whether the series are non-stationary. The ADF and Philip-Perron test results also mentioned here, right? Is the levels and the first difference. Then this augmented Dickey-Fuller test and Philip-Perron test also shows that first difference series are stationary. Right, after that, that is the first step we need to do to check the series stationary. Then the second step is identification of the model. We need to identify what our model is. We can use the correlogram of figure 1. In the figure 1, here, figure 1 to determine the model of autoregressive moving average, to determine the P and Q. That means value of the parameters of P and then value of the parameters of Q. As already mentioned, ARP model has a PACF at a lag P, and MAQ has the ACF that indicate at lag Q. In practice, plus or minus 2 over number of sample size, square root of sample size are the non-significance limits for both functions. Right, to do this, we shall use the automatic model determination criteria, Akaike information criteria, AIC. AIC means Akaike information criteria. SIC means shows information criteria. The limits for both functions ACF and partial autocorrelation function PACF are plus or minus 2 over sample size is 35, square root of the sample size. This is plus or minus 0.338 from figure 1. The ACF cutoff at leg 2 0.338 here this value is greater than the 0.338 leg 1. That is the limit. From figure 1, ACF cutoff at leg 2 Q equal to, and the PACF at leg 1 P equal 1. Right, this one value is 0.338. This value is greater than 0.338. This value also greater than 338. This is less. Then there are number of legs are 2 according to the ACF. According to the PCF, this only the first leg value is greater than the 0.338. Then it's a value leg number of Q is 1, P is 1, Q is 2. Then the range of model AMA PQ is 0 and 1, or the Q 0 or 2. For the optimal on the basis of AIC and SIC. So we create table 2 with the value of P and with the value of Q as follows. Then the P0 Q1 Akai information criteria is 4.92, so as information criteria 4.96. When the P0 Q2 is 4.9 and then 4.99. In both 1 and 0 this is, and then in the 1, so then that is Akai information criteria is 4.88, it is 4.95. The table 2 indicate, this table indicate that according to these two criteria, Akai information criteria and SWAS information criteria, the model autoregressive moving average model is formulated AMA 1, as the model is stationary on first difference. Then D is 1, then ARIMA is 1, 1, 1. ARIMA is 1, 1, 1. Then we estimate the model. Therefore, we can proceed to estimate about above model. We estimate the ARIMA model 1, 1, 1. Then this table shows this is the EV output of the ARIMA model. Both coefficients are statistically significant. Both coefficients are statistically significant. See the probability statistics in these two columns. In this column T statistics column, AR1 and AR1 and the variable MA1. these two variables are statistically significant because the probability values corresponding to the t statistics are less than 5%. Then we are writing that the first difference DGDP equals 0.6831 DGDP minus 1 minus this is MA is error 0.9514 ET minus 1 plus ET. On the following diagram, the inverse root of AR and MA, that means autoregression and moving average, characteristic polynomials for the stability of ARIMA model are presented inverse root of AR and MA. All values, all dots are inside. From diagram 3, we can see the ARIMA model is stable since the corresponding inverse roots, AR roots and MR roots, both are in the circle. Then the next step is diagnostic check-in of the model. The diagnostic check-in of the model help us to check the estimated model, whether our estimated model is acceptable or the statistically significant. That means our residuals are autocorrelated and then follow the normal distribution. For checking the autocorrelations, we use Q statistics, and for normality test, we use Jack-Berra test. The results shows that histogram of the residuals, Jack-Berra statistics. Figure 5 shows the correlogram in the ARIMA model. Residuals of our ARIMA model follows normal distribution. The probability value, it is greater than 5%. Q statistics shows that value greater than 5%. Then there is no autocorrelation for the examined residuals of the series. Then this model, we can determine that this model is suitable for forecasting. Right, this is the forecasting results. The results in this figure 6, you can see that inequality coefficient of this figure shows high value U is 0.9. Here this inequality coefficient is 0.0902. That means our model does not have good forecasting ability. The table 6 below summarize the forecasting results of the GDP. Then the residuals minus 618. Here in model 618. . 618 . and 2013 and 14, then the first difference series and the normal values for forecasting for 15, 16 and 17. Right, then what this article explain, by using the ARIMA model or by using the Box-Jenkins methodology for forecasting future sales. Right, this is the way we use to forecast future sales, for forecasting the prices, for forecasting inflation, for forecasting share prices. This is the method, right? This is the way we used. This example forecasts the real GDP rate for the next 3 years, 15, 16 to 17. Then the GDP rate for year 2015, 16, 17 is forecast to be 1.56%, 2.85% and 3.12% respectively. Right, these results will help for the policymakers to formulate effective policies for attracting investment, domestic and the private, private domestic investment or foreign investment. Also, these results help the managerial business executives for implementing the new project ideas or taking decisions concerned with the expansion of the existing business. Right, so let's apply the EV file, download the EV file, go to the LMS and download the EV file and follow these steps. Right, in this data file, there is a GDP, real GDP data here. Right, open, this is the real GDP, quarterly GDP with you. First, check autocorrelation function. Right, follow this step first. Right, this is Box-Jenkins methodology. Apply this Box-Jenkins methodology. First, go to the correlogram of the real GDP, correlogram. Go to the quick, series statistics and then go to the correlogram. Right, series name is RGDP. Click OK. First, we need to see the correlogram in levels. Click OK now. This is the output. Copy and then paste in a Word file. Right, in this case, you can see the Q statistics. You can see now this Q statistics and then probability values corresponding to this Q statistics are less than the 5%. That means our levels data are non-stationary. Then go to the first difference series of the data. View, correlogram. Go to the first, select correlogram of first difference. Now click OK. This is the copy is okay. Right, this is the first levels data, autocorrelation function and the partial autocorrelation function. The second difference series also the non-stationary. Then go to the correlogram for the second difference. Second difference also the non-stationary. Right, second difference series also the non-stationary. Now we can do something here, because in the first levels data non-stationary, first difference series also the non-stationary, second difference data also non-stationary. Now there is a remedy for that. First see the graph of the data series. Graph the series, quick and graph the GDP. Basic graph. This is a trend. Copy and paste it. Right. Now there is a trend in. Now generate the series, convert the data series, log RGDP equal log RGDP. Right, there is a variable here, LRGDP. Now check the correlogram. LRGDP. First difference. Right, this is the first difference, not first difference, that is the ADF. It's undo. Copy and the paste. The probability values relating to the Q statistics are less than the 5%. It means that the series are non-stationary. Then go for the first difference. First difference. It is also the non-stationary. Then go for the second difference. It is also non-stationary. Same thing happened. But here in this e-views, for the go for the next differences, there are no options. Shall we include more legs? What to do this? Series are non-stationary, but this is the problem. The series are not series are non-stationary in the first. Let's see that quick correlogram LRGTP. Right, anyway, assume that the series are stationary, then follow the next step is go to the file and check quick series statistics unit root test. Series is LRGDP. Then go to the levels, select levels, and then there is a trend and the intercept. This is the unit root test, augmented Dickey-Fuller test results. This is a LRGDP as a unit root in levels. Now go to the first difference. First difference. In first difference, the data shows that there is right, but in the augmented Dickey-Fuller test and the Phillips augmented Dickey-Fuller test shows that in the log value of the real GDP, first difference are stationary. Then do the test, unit root test, Philip parent test. First go for the levels. Levels are non-stationary. Right, when see that the probability value is greater than 5%, then that means our GDP has the unit root. Then go to the first difference. First difference. The both test. Right, both, but here the probability value is 0.000. That means Philip-Perron test shows that second difference series has not a unit root. That means first difference series are stationary. Right, now go for this is the test results of augmented Dickey-Fuller test and the Philip-Perron test. Shows that GDP logarithm of the real GDP is stationary. Now, identification of the model. For this, we use here two limits of both functions, augmented Dickey. To do this, we shall use the automatic model determination criteria, Akaike information criteria and the source information criteria. So, need to determine the number of Q and number of P. Then plus or minus 2 sample size in our model observations is 64. Right, then what is the value? What is the value for that? 64 square root of the 64, 2 divided by the right, it is 2 divided by 8, 1 divided by 4, it is plus or minus 0.25. Right, go to the table. Number of parameters P and then number of parameters Q. So, MA in the model, a quick series statistics parallelogram. the levels there are more than 10. This value or AC, the value is higher than up to the 10th leg. PAC up to the, let's see that in figure 1 that our limit is 0.25. This graph shows the correlogram. Let's see the 20 levels. This is cut, copy and paste in a Word file. Our value is 0.25, right? 0.25 up to here. So then leg 13. Then AC legs are 13 and then PAC is 1 because only this value is greater than this. MR value is, AR value is 13, MR value is 1. Right, where difference D is also 1. Then how to write the model? We need to use the 13 legs and MR only 1 leg. How to write the model? Y equal A A1 YT minus 1 YT minus 1 right A1. A means that I put here for the coefficient A1 YT minus 1 copy plus A2 YT minus 2 and write the model A3 up to 13 YT minus 3 right up to A13 YT minus 13. Then write the model plus 1 MR Then in this article you can see this here. This is the model T minus 1 in our 13 autoregressions. Then minus u T minus 1 plus u or error T. Right, this is the model 13. Then our ARIMA model we are writing like this. ARIMA 13 autoregressions, 1 press difference and 1. Right, this is the way we are writing our ARIMA model. ARIMA autoregression 13 autoregression, 1 press difference, then our ARIMA model is our ARIMA model will be here. This ARIMA model is 111. In our ARIMA model is 1311. Then we need to estimate the model. We need to estimate the model. Go to that. Go to the work file. Here, quick estimate equation. Log R GDP equal right here. We are writing estimate equation. Our variable is log LRGDP equals, no, it's constant AR1, AR2, AR3, AR4, AR5, AR6, AR7, AR8, AR9, AR10, AR11, AR12, AR13 plus MA1. Yeah, it is. Right, this is the model. Our dependent variable should be not right. This is first difference of the real GDP, log of real GDP. If for roots, go for the view. Here, ARMA, autoregressive moving average structure, select. Then there is a roots, it's a graph. Right, there is a AR roots and MR roots. Copy and paste it. But show that in the article shows that inverse root of AR and MR, inverse roots of AR, MR polynomials. This diagram shows that all roots are in the unit circle, are inside, but in our model, only 3 roots are in the margin, all are in the roots. Now we need to check the diagnostic check-in, histogram and the correlogram. Go to that view, residual test, correlogram. its correlogram. Also go for the weave residual test, histogram, normality test. Now see in the article, but in our model, ARIMA 1311 model, the normality test, it is violated. Jack-Vera test shows that there is no normality. Right, there no autocorrelation in this, but in our case, there is a normality issue. Also, this probability value is less than 5%. It has a serial correlation as well. But in this model, OLA, you can see that these are more than 0.05, then no autocorrelation. The probability value also greater than 5%, no autocorrelation. But in our data set, there is an issue. Right, anyway, so then need to follow this process. Then forecasting. Right, for forecasting, go for here, there is in the data output, there is a button here called forecasting. Again, go for the estimate equation. Therefore, then go for the forecasting. This is the forecasting. Go for here forecasting our RGDP, forecasting name, logarithm for forecasting. Insert actual values for estimated period. That this is the forecasting output. Go for here and then the forecasting output. Oh no. Copy. It is still inequality coefficient is 0.16. In the article, you can see forecasting for the ARIMA model. The results in figure 6. This 6 shows that inequality coefficient is 0.9. Means our model does not have a good forecasting ability. Then right. Now follow the same procedure for in the same data set. Right now you can understand how to use the Box-Jenkins methodology for forecasting purpose. Right, in the ARIMA model, this is the preparation. This is the data preparation plot. If you have a data series for forecasting, First, plot the data and examine the stationarity by using correlogram. That means, that examine the autocorrelation function for stationarity. If not stationary, take first differences. Take first differences of the series. Then examine the again autocorrelation function after these transformations. Normally, in time series data or the finance data, before taking the first difference, transform the data series to the logarithms. Examine then after converting to the transformations, then examine the autocorrelation function to determine the series are stationary or not. The next step is model identification. In the model identification, examine the autocorrelation function and the partial autocorrelation functions to get some idea about the value of the P, the number of autoregressions. D means how many differences, first, second or third. But in the software package, we can use second differences. Q means number of moving averages model to estimate. Then estimate the model. After examining the model, by using the information criteria, test the white noise for the residuals. Then this model can be used for forecasting. This is that first plot the raw data to indicate that the series are non-stationary. This plot of the autocorrelation function, this is non-stationary series because the autocorrelations, this graph shows diminishes very slowly. This is the first difference series. This is the autocorrelation function series. This series, we can see that it's fairly decreasing very quickly. Then we can see that first difference capacity, first difference of the series is stationary. Here, important thing is how many P. P means how many autoregressions. It determines the partial autocorrelation function. Also, moving average, it use more number of moving averages, and D means first difference. For forecasting, we use the Box-Jenkins methodology. In Box-Jenkins methodology, we capture the past pattern and then forecast for the future. This is an example. We use ARIMA model for Then important concepts in the ARIMA model. Important concepts of the ARIMA model are stationarity, and integrated variable, whether series are stationary in the first levels or first difference or second difference. Then the AR process, then the MA process, then the AMA process. AMA, if you use AMA, PN, only the P and Q. Number of autoregressions, number of moving averages. If ARIMA means P, that means number of autoregressions, number of differences, and number of moving averages. Then autocorrelation function, and then partial autocorrelation function, white noise, and autocorrelation, model efficiency autocorrelation, then the steps in the ARIMA model. There are many steps in the ARIMA model. Steps. ARIMA model. This model is used for forecasting sales, for forecasting the prices, for example, for forecasting the prices of the rice, for forecasting the sales, forecasting inflation, forecasting the inflation, forecasting unemployment, forecasting GDP. Right, this method is used for this for forecasting. First step is in the ARIMA model is model identification. Model identification. For model identification, what you need to do is check the autocorrelation function, ACF, and If first check if the autocorrelation function uh, cuts off, if the autocorrelation function cuts off fairly quickly or die down fairly quickly, then the time series data are stationary. If the autocorrelation function dies down extremely very slowly, then the series are non-stationary. Right, so then if the model identification also instead of the autocorrelation function, we can use the augmented Dickey-Fuller test as well as Philip-Perron test to check the stationarity. Then next step is auto-regression, regressive integrated moving average model. Model estimation, model identification, then model estimation. By using this, we identify our model, ARIMA model, what number of P's, number of D means first differences, first or second, and number of moving averages, PDQ. It are all are simples. P means number of autoregressions, right? P means number of autoregressions. Number of autoregressions. D means number of difference. D means difference, first difference. If it is first difference, we use 1. If it is second difference, we use 2. If it is levels, we use 0. For example, in levels, assume that all series are stationary and levels, then D is 0. Right? If series are stationary in first difference, then D equal 1. If the series are stationary in second difference, then D equal 2, like that. Q means number of moving averages. Assume that P number of autoregression is 2, D is 1, D is 1, and Q is 1. Then how to write the model? Assume that our first difference, because of the first difference, then our dependent variable is dy equal alpha. We can write alpha. It is I'm writing here for alpha e plus a1 y dy minus 1 plus a2 dy minus 2 minus, right, d is in here, a means it's a constant, a1 a2 a1 a2 are the coefficients, a2 are the coefficients, uh, d means plus difference, y minus 1 y minus 2 means that number of autoregressions. Then here q, it is the errors, it's moving averages, it is a3 ut minus 1 u minus 1. If it is assume that for q is 2, how to write it? Minus a4 u minus 2 plus e, that is the error, right? This is the way we are writing our model identification. How many autoregressions, how many differences, how many moving averages. Here A1, A2, A3, A4 are the coefficients. Then first leg of assume that dy means our GDP, right? Assume that this is GDP. Then dy minus 1 means leg of the GDP. It is leg of the second leg of the GDP. This is the error term, errors, leg of first error. This Q moving averages. It's a second leg of moving averages. After model identification, the model estimate the parameters, then estimate all parameters. This is what the parameter means: a1, a2, a3 and a4. What are the value of these parameters? This is the model estimation. Then estimate parameters. For a tentative model. Then third step is model check-in. Model check-in is autocorrelation and autocorrelation by using ACF. That we use the Q statistics. Right, if the Q value, Q statistic probability value corresponding to the Q statistics is small. For example, probability value less than 5%, less than 5%, model is considered inadequate. Model is inadequate. Then the analyst consider new model, a new or modified model, and continue the analysis until a satisfactory model has been determined. Right, in our GDP model, it's inadequate for forecasting because the probability corresponding value for the Q statistics, you remember, it is greater than, it is less than the 5%. This probability value less than 5%. Also, the Jagbera test shows that no normality. Then we cannot, model is considered inadequate. Then the researcher consider the new or modified model and continue the analysis until the satisfactory model has been determined. Also, we can check the randomness of the residuals. Residuals by considering graph of autocorrelation function and the partial autocorrelation function of the residuals. The residuals autocorrelation individuals residuals autocorrelation should be small and generally within the number 2 plus or minus 2 divided by the square root of n. Square root of right. In our example, it is this value is 0.25. Right, for example, in our previous example, it is 0.25, and then go to that our autocorrelation ACF and PCF, that value are residuals, autocorrelate small, are all very small. Right, these are very small in this ACF, and then PCF also, it's very small. Then then step 4 is, fourth step is forecasting with the model. Then forecast for one period. You can use this our estimated model, forecast for one period, several periods into the future. Parameters for a model has been selected. In our here in this model, this is our ARIMA model. Right, so in this is, those are the This is the method for forecasting sales or forecasting future prices or for forecasting future GDP, whatever. So then this is in a discussion questions. And what is the main difference between the form of AR, auto-regression, and MR in time series model? Right, B practice ACF plot and its interpretation and how it interpret. And check how many determine the AR, number of ARs, number of D, that means P, D, and Q. And check the validity of the ARIMA model. Right, using the same data set, there is select any finance related data or the share prices. For example, how to forecast the share prices by using the Box-Jenkins methodology. And for this purpose, follow the Box-Jenkins methodology, keeping this article with you, and analyze first the correlogram for the levels. Here for correlogram test for the levels. Here correlogram test for the first differences, and the augmented Dickey-Fuller test and Philip-Perrin test. These are the summary of the results, not the EView results directly to here. Then check the model, ACF, PCF, limits of both. This is the formula to find the limits. Check the ACF, PCF are in this range. Based on this, we can identify the number of ARs, number of MAs. Then estimate the model. Estimate the model, write down the ARIMA model by using this information. Here then AR1 means GDP, it's a lag of the GDP. MA means, in this example is minus, that is MA, it is the error term. Then check the roots, whether all to check the model stability. Then the diagnostic check-in for normality by using the Jack-Bera test. If the Jack-Bera test probability value corresponding to the Jack-Bera test should be less than greater than 5%. If it is less than 5%, it shows that there is a not normal, there is an issue in the normality. Also the correlograms residuals of the model, if correlogram residuals, these values should be greater than 5%. If it is greater than 5% means there is a no autocorrelation issue. If there is a no autocorrelation issue, then the model can be used for forecasting. If in our example we consider if there is a issue, so then we can't use this model for forecasting. But understand the way, the methodology we use for forecasting. Right? And, next week, let's discuss some practice questions from the beginning. At the beginning, we discuss the starting from the model efficiency, multiple linear regression. We start the multiple linear next session. Right, discuss some practice questions. Right, starting from multiple linear regression. Right, then checking the model efficiency. That means heteroscedasticity, normality, and etc. If you have your own data set, bring your data set for running the multiple regression, for checking the model efficiency. Then if the series are time series, then stationarity, check-in stationarity, check-in co-integration, and check-in VA or vector error correction model, and check-in the causality. So we couldn't do it. By discussion questions, I cover the causality test as well. Then finally again forecasting by using ARIMA model. Right, those are the topics we discuss. Here also we discuss impulse response functions under, it is under VAR. And the forecasting using ARIMA model. Those are the topics we discuss. The coming to two lecture series, I plan to discuss some practice questions relating to the topics we have discussed so far. Thank you very much. It's here the diagnostic yeah, if the diagnostic results are not accepted, then we need to we need to go back and re-estimate the model. Re-estimate the model if diagnostic results shows that our model is inefficient, then this model cannot be used for forecasting or for interpretation as well. Then again go back to the data series and then check whether we gather the series correct way or the transform data to the natural logarithms. I transform the data to the logarithms. Now we need to check that whether we convert this data to the transform the data to the natural logarithms, and again check the stationarity, again check the stationarity, estimate the model and check the efficiency until our model fulfilling all the criterias, all the model efficiencies. We cannot use the model for forecasting. If we use the model for forecasting, the results are not, or the conclusions are not realistic. That's why, as a remedy for that, again go back to the data set series, check whether we collect the series correct way. Also, we transform the data in natural logarithms and then rerun the model. Hope you can get the answer for this question. Also, your data, Vitanage, your data set, you told me that it is multiple regression. The next week, bring your data set and analyze your data set and check the model efficiencies until uh, diagnostic results becomes okay. Okay, today is due to the funeral of the relatives of the our technician, so then I will have to stop the lecture today, and then next week I will discuss discuss the same topic what we have discussed so far, and discuss some practice questions relating to the each topic as well. If you have any questions, it is okay to ask. How is your assignment? How is your assignment? Right, if possible, next week, if you can upload the data set, I can use the same data set for running the multiple regression and then for checking the diagnostic, check the residuals, errors or the diagnostic test. If possible, is it possible for uploading the data set by next week? It doesn't matter. Now, sample size maximum 30 is enough for analyzing. Okay, then please upload by next week. So then I use the say that your data set for running the multiple regression as well as for checking the diagnostic test. Also for if possible, so then I can use for other for forecasting purpose as well. Okay, then thank you very much for participating in the lectures and then be interested for the analyzing your data set. We'll see you on next week then. Thank you.